Okay, we're recording. All right, time to get started. So, last time we were talking about linear approximations, and we wrote down a formula and outlined the process by which you can confirm that it has all the properties that it's supposed to have, but all of it, you may recall, was subject to a gigantic if. This was all assuming that the linear approximation exists in the first place. Right? Here's the thing. I mean, you can write down formulas, like you can write down this formula for single variable linear approximations and this for a multivariable but still real valued function, linear approximation, et cetera, et cetera. Let's see, I guess, where's our final formula? Here it is. This is the general final formula. I can write this down. I can play games and confirm that it's, has all the right properties, but this assumes that there's a linear approximation in the first place to be correct. So let's entertain now just a little bit. But is it really? Did this really work? Or was this all speculative? Here we go. I'm going to address this with and real quick. I want to mention this conversation about differentiability is a long, deep conversation. That's really, actually, honestly, a full discussion, not really appropriate for Math219. So what I'm going to be giving y'all is hitting the highlights. We're going to go very quickly over the details. You're not going to be responsible for the stuff that I'm going to be skipping over, right? So this is going to seem quick, right? But that's just what we have to do in this class. Okay, all right. So example to start the show. Here is a function, perfectly good function. A little bit weird looking in the way we write it down. There's nothing really wrong with this. What we have down here is a graph of this function. And notice, for example, let's see here, when x is 0 or when y is 0, in other words, for these points in the domain, the value of the function is 1. Thus putting the graph kind of up there for those values in the domain. The function is then defined to be 0 everywhere else. So all of this space over here in the first quadrant, fourth quadrant, let's see here, third quadrant, second quadrant, etc. The function is defined to be 0 everywhere other than on the axes, and on the axes the value of the function is 1. So, weird, but perfectly legal. And now let's ask the question, this function, what is the linear approximation at the point 0? And if I want to compute that, well, I can compute the value of the function, no problem. The value of the function is 1 when you're at the origin. Can I compute the partial derivatives? For example, what is the partial derivative with respect to x at the origin? I remind you, and keep in mind the origin right here. Well, the partial derivative with respect to x, there's nothing to it. There's what the values of the function look like when you are at the origin and moving in the x direction. They're just 100% flat. Right? It's constant. When you're at the origin and moving in the x direction, the function doesn't change at all, and that partial derivative is 0. No asterisk. It's just 0. And then likewise, what's the partial derivative with respect to y when you're at the origin? Well, when you're at the origin moving in the y direction, the values are constant again. And so that partial derivative also 0. And so based on what we have here then, looking at the origin, here's the value, let's see color choice. Here's the value of the function and the values of the partials. And based on that, we write down this function L, our otherwise would-be candidate linear approximation. And based on the formula we wrote down last time anyway, this is what we would get. Now I have to ask, did this work? Is this really a good linear approximation to this function? No, it's really not. The value 1, constant value of 1, is a terrible linear approximation. Because while it does a good job of approximating what the function is doing up here where the value of the function is 1, don't forget the value of the function is flat 0 down here. So this is a terrible linear approximation, right? If you're looking at a point down here in the domain, let's see here, I'll use dark blue. If you're looking at a point like, let's say, right there, and you imagine that you're proceeding toward the origin, the value of the function is 0 the whole way toward the origin. The, quote, linear approximation that we've written down here, its values are 1 the whole way towards the origin. This is not doing a good job of approximating the function. Does everybody see where this stinks? Right? This is unacceptably poor. We can't in good conscience call this a linear approximation of the function. Okay, so this is why I had to be, cautious and, hey, we're going to assume it's existing because who knows, maybe it doesn't. This kind of nonsense here this is one of many examples of the kinds of things that can go wrong. Okay, so what we want to do now is come up with a better, more sort of complete way of addressing this question. Does a linear approximation exist? Or said differently, if I find a candidate linear approximation, how can I decide if it actually is? Or if there's this kind of garbage going on. So let me throw out a proposal, reasonable first proposal. Let's look at error. Let's look at how far off is our linear approximation. Namely, what's the difference between the actual value and the estimated value, the approximated value. That difference is the error. Wouldn't it seem reasonable that the error should just approach 0? Isn't it good enough to just require that the error approach 0? After all, error is the thing that's bad. If the bad is in the process of disappearing, I don't know, casually it seems reasonable, right? Now, this is a reasonable first attempt, but I emphasize this is actually not a good test. And the reason it's not a good test is illustrated by this example here. Let's just actually do it. Here is a function. I don't even have to go multivariable for this. This is just a single variable function. There's the graph. And now I'm going to propose, knowing off the bat that this is preposterous, I'm going to propose this as being a linear approximation, and let's see if the test appropriately rejects this ridiculous candidate. Look at it right there. So there's the alleged linear approximation to that function. Come on, it's way off. It's not even going the right direction. That's ridiculous, right? Well, our test up here had better reject this candidate, right? Defining error as such. Does the error approach 0? Well, it does. Here's the error. That's what the error is. And as x approaches a, this error does indeed approach 0. So as far as this test is concerned, we've got a good linear approximation to our function here, and clearly this means our test stinks. Does everybody see why that's bad? Okay. All right. So, like I say, it was a reasonable first attempt, but we realized quickly that this is unsatisfactory. What we're going to do instead is we're going to insist that the error approach 0, what I'm going to call faster. So not just the error will be approaching 0, but what we call relative error. Relative error says I want to look at how the error compares with how the error compares with how far I am away in the domain. And as I get closer and closer, as my distance from my base point gets lower and lower, I want my error to be approaching 0 faster even than that. Example. Same candidate that we were looking at a minute ago. Here's our function, 5x. Here's our preposterous candidate linear approximation, which had better fail. Right? We know this is bad. Casual glance. This is clearly bad. We want our test to reject this candidate. And, well, okay, let's see what happens. Here's our error, just as it was before. But now I'm going to, per the definition of relative error up there, I'm going to divide by how far I am away from the base point. And as x approaches a, not only do I want the error to approach 0, I want the error, even in comparison to the disappearing distance, horizontal distance from x to a, even in comparison to that, I want even this fraction to approach 0. And let's see what happens. Easy little bit of algebra here. And this expression, you plug in the numbers, and, it ends up being 2, which is not 0. That's really the point. So, wait a minute. The test was the relative error would need to approach 0. This one doesn't. And so, as it should, this rejects that as a candidate linear approximation. So, we've made some progress here. Is everybody happy with how this is better? Yeah.
Just a quick question about the limit itself. Mm-hmm. Are you using limit as x approaches 0 because a is 0 in this case, or is it always?
Yeah. No, x as that's right. X approaches a. Yeah, that's right. Yeah, maybe I'll go in and change that. Yeah, that should be a. Which is 0, so it's not like this is wrong, but yes, in general it's a. That's right, yeah. Okay, so this is what I'm going to call the moral of the story. If you want to be able to use, if you want to test, if you want something to have to go to 0, what you need is for relative error to be the thing going to 0. And that leads us to the actual definition of differentiability, namely the definition of what it means for this to be a good linear approximation. And the definition is that the relative error approaches 0 as x approaches a. Now, I will confess, what we have in purple here is a statement about a limit, a multivariable limit. We kind of skipped that section, didn't we? The way that we're using it here, it means exactly what you would guess it means. How to make that formal and precise is another one of these topics that, tough choices and all that, we just can't really include in this course. We just don't have the time. It's not really the focus of the course. This is more of a course about geometric intuition and computation and this problem solving, that kind of thing. The rigors and formalities of the definition of a limit are just not really what this course is about. So anyway, don't worry about that in this context. Here, when I say approaches 0 as x approaches a, it means exactly what you think. Okay. So that's the definition. Now, just to stretch that out, reminder, that's what relative error is defined as. Another little quick reminder, that's what error is defined as. Another little quick reminder, let's see here, and I'm going to have to play some parentheses games here. Bear with me a moment. I'm going to need to see. I need to put this in parentheses here, but that's going to make that minus distribute. So I really need to make this a plus just to make this work out what I'm about to do. Don't forget that L is this thing. Right? So when we say that we want the relative error to approach 0, I mean, fleshed out completely, I need for this thing here to approach 0 as x approaches a. So that's how you're going to see it written down in a lot of books. And you look at this big fraction at first, and you're like, oh my God, there's so much going on. It's a little overwhelming. Where did that come from? It's relative error. That's it. It's just a way, it's a fully fleshed out formula for relative error. Yeah.
So if all of x turns out not to be a good linear approximation, is there a possibility that there's another linear good?
No, that's a great question. If there is a satisfactory linear approximation, then this will always be the correct formula. That much is true. But this formula does not always satisfy this deeper requirement about vanishing relative error. Right. So there's no other formula that you should have to concern yourself about.
So essentially, linear approximation doesn't exist.
Correct. If this limit does not approach 0, then there is no linear approximation. There's no reasonably, good linear approximation. That's right. Okay. So yeah, I just think it's a healthy thing to know, if only culturally, right? I mean, you're not going to problem solve with this. Certainly not in Math 219. But it's good to know where this expression comes from and why we care. It's really ultimately, not that surprising of a statement once you see where it comes from. Now, the other thing I'm going to do while I'm here, we wrote this as being the value of the function minus the value of the approximation. Sure, reasonable. I just want to point out also, though, that you can also move parentheses around in a different way. And you can realize this numerator as being how much the function actually changed minus our linear estimate of how much the function changed. So actual minus estimate is same story, same expression, same actual value there for the numerator. You can just think of it in this slightly different way. And this is useful terminology. So this linear estimate of how much the function changes, that's called the differential. It's a good general fact. The term differential means a linear estimate of how much the function changes. That's all it is. And by comparison, the actual amount the function changes is called the increment. So these are good terms to be aware of. I might use them here or there, and heads up. Okay, so wow, how annoying. Differentiability, the definition at least, is bulky and awkward. Nobody likes that. So in practice, day in and day out, how do we use differentiability? And by the way, kind of just scary news. We need to use differentiability a lot. There are a bunch of theorems that we're going to encounter in this class where the condition is differentiability. In other words, what you have to check or know before you can apply this wonderful theorem that you're going to want to be able to apply, you need to know the function's differentiable. And at a glance, then it kind of makes it look like, oh my gosh, I'm going to have to deal with this every time I want to use a cool chapter 2 theorem. So that's scary. Here's the good news. There is a much easier little workaround that's based on a different idea called continuous differentiability. This is a different thing. Let me first define it, and then we'll talk about how it relates. What we mean by a function being continuously differentiable. Much simpler to say. Really simple to write down the definition of continuous differentiability. It's all about the partial derivatives. They just need to exist. That's easy. Partial derivatives are super easy to compute. Just write them down, confirm they exist. And then they need to be continuous. And I'll remind you from single variable calculus, something is continuous. There's various different ways to say it, but we have all these powerful theorems about, for example, all polynomials, all continuous. Trig functions, wherever they're defined, that's an important asterisk. Right? They fail to be defined in certain points, vertical asymptotes. But where they are defined, trig functions are continuous. Logs, exponentials, practically every function you can think of, practically every function you can make with every function you can think of are continuous where they're defined. There's very few functions that fail to be continuous where they're defined, at least in terms of what we typically work with, algebraically. So I'm going to say it's easy to check when the partial derivatives exist, and it's easy to check at a glance when they're continuous. So continuous differentiability is really easy to define, and here's why we care. Keep in mind, differentiability is what I really need to know. There's going to be a bunch of theorems where, okay, I need F to be differentiable. The way in practice, most of the time, you're going to check differentiability is you're actually going to check continuous differentiability, which is easy to do. Just, again, take the partials, confirm they exist, confirm they're continuous. Nothing to it. And then you're going to cite this theorem that says because the function is continuously differentiable, it must therefore also be differentiable. This theorem is hard to prove. We're not going to prove this theorem in this class, but you do get to cite this theorem in this class. So this is a very powerful, very useful, very convenient tool. So example. Let's look at this function right here. Let's ask the question, is that function differentiable? Okay. Step one, I got to compute the partial derivatives. In fact, technically I don't even really quite need to compute them. But I need to be able to persuasively argue that they are polynomials. Which is pretty clear, I think. Polynomials are all continuous. They all exist and they're all continuous. So this function is continuously differentiable, and therefore it's differentiable. It's that easy. Everybody happy? Okay. Now real quick, I do want to comment about, y'all heard me say this before, you're going to hear it a bunch more times going forward. It's not about the answer, it's about the reasoning. Right? So you do have to document the reasoning. Proper, appropriate reasoning does need to show all of the significant steps. Right? And I think what I've written here is pretty bare bones. I don't see how I could write this proof here any tighter than this. So if you take out any one of these steps, then I think you're taking out a significant point. So, for example, it would be tempting to say, well, the partials are all polynomials, so therefore it's continuously differentiable, and therefore it's differentiable. Well, wait a second. How do you know that polynomials are continuously differentiable? Where did that come from? Well, it comes from the fact that the polynomials are continuous. That's the point. That's what makes polynomials continuously differentiable. Right? Does that make sense to everybody? So you're really going to put that in. That's a significant part of the reasoning. So make sure to put that in there. Another common mistake that I see let's see, what's the word? Common omission that students will make is they'll say, okay, well, the partials are polynomials, all of which are continuous. So therefore the function's differentiable. Again, all true, but there's a big point missing in the reasoning. The reason that the partials being continuous means differentiable is because of this very significant idea of continuous differentiability and the very significant theorem that it implies differentiability. So be careful, right? Make sure to document all of the relevant points in the reasoning. You can be terse. Look at this. What I've written there was two sentences. One sentence. Okay, 2 lines. Right? But this is pretty terse. So just don't try to be too terse. Right? All of the relevant points need to be documented. Okay. All right, now here is another fact. This is also useful. And again, we're not going to prove this first statement, but every differentiable function is continuous. I think it's pretty believable. Y'all saw something like this in single variable calculus. In this form, it's not all that useful for us because it assumes an answer to the question about differentiability. But we can do what's called the contrapositive. The contrapositive of P implies Q is not Q implies not P. Right? If you kind of think it through, they mean the same thing. They're just kind of grammatically different. Like one is active tense, one is passive tense, or something like that, something along those lines. But they mean the same thing. And now, check it out. We have a theorem, the conclusion of which is an answer to the question about differentiability. This time in the negative, but still it's an answer to that question. So if you can detect whatever it is the case, that your function is not continuous, boom, you instantly know it's not differentiable and you don't need to play continuous differentiability games. So easy example is this function we started today's class with. That function right there. It's clearly got a discontinuity. Casual glance. And that discontinuity means it cannot be differentiable. Everybody happy? All right. Okay. So now we're just going to kind of wrap up some stuff we've morally really kind of already done. I'll remind you that this is our formula for a linear approximation, but now we are armed to say a little bit more precisely that not only would this have to be the answer if the answer were to exist, which is where we left off last time, but now we can say very simply, if the function's differentiable, then boom, answer. That is the linear approximation, and it does what it's supposed to do. Okay. So now I'm just going to kind of move things around a little bit. One of the criteria of a linear approximation is that it has the same value as f at the base point. And now I'm going to take this and move it over to the other side. Didn't really hardly do anything yet. But look what we've got now. What we have over here on the left represents how much the input to our function f is changing. And over here on the right, we have literally our linear estimate of how much the output of the function is changing. So in goes what we call the input differential, what I call the input differential, and out comes the output differential. So this thing here is doing something extremely natural. That matrix df, which previous to now was just a notational shorthand, a bookkeeping tool, this turns input changes into output changes. That is you may recall the very first thing that we said when we started talking about derivatives a couple days ago was that's the sort of the defining characteristic of a derivative, something that turns input changes into output changes. So this does that. This does that in general, no matter how many input variables you have, no matter how many output variables you have. This is the thing that turns input changes into output changes. So this is the thing that we call the derivative. Now, that is a weird thing to hear for the first time, because in calculus, single variable calculus classes, the derivative, I'll say it this way, the value of the derivative was a number. The value of the derivative represented something geometrically, namely the slope of the tangent line to the graph, to blah, blah, blah. But it was a scalar, it was a number, right? It was we always thought of derivatives as being just a number. We're going to have to calibrate, reinterpret in a multivariable context. No longer can you or should you think about a derivative as being a number. Most fundamentally, a derivative is this thing. It's a matrix. Or, depending on who you're talking to and how general you want to be, it's the linear transformation defined by this matrix, and we call it the derivative transformation. Or, again, if thinking of it as a matrix, sometimes people say the derivative matrix. So, like I said long ago, there's going to be different kinds of derivatives that we're going to see in this class. We've already seen partial derivatives. We've seen the gradient vector. We've now seen the derivative matrix, aka the derivative, right? That's 3 of them. And we got at least one more coming. And depending on how you look at it, arguably several more. But philosophical. Yes, question?
I just had a question about what the difference was between the output differential, like Lx minus La, and the increment that you defined earlier, Fx minus Fa.
So L is a linear approximation. F is actual. So, the L's job is, look, the function itself, I don't know, for whatever reason, I can't really compute the actual values of the function, right? So the increment is arguably what you actually care about, but it's inaccessible. You don't know what it is. I don't know how to deal with that, right? So it's arguably the goal. The differential, L of x minus L of a, is our best estimate of that elusive increment. Does that make sense? Yeah. I mean, you think about single variable calculus, it's the same deal, right? I mean, function, like how do you estimate the value of sine of 0.0001? Right? I mean, but linear estimate is something we can actually do. Yeah. Everybody good? Okay. All right, so here's my pick. Oh, and then real quick, a notational thing about the derivative. So this thing, df, the derivative matrix, sometimes is written with a J, and that's because it's referred to as the Jacobian, named after a mathematician named Jacobi. So anyway, you're going to see at some point in your future, you might see JF. It's df, whatever. Same thing. Okay. So here's a kind of a picture of what the derivative transformation does. Suppose we have some point in the domain A, and it has some image over here, f of a. So you might say that the function takes that point to that point. Oh, by the way, notice this is not a graph. This is not a level set. This is not a parameterization, right? This is what I call the literal picture of the function. I've got the domain on the left, the target on the right. Okay, so green point goes to blue point, and here's what the function does. The function takes points in the domain to points in the target. Now let's think about what the derivative transformation does. If I had some differential in the domain representing, I'm going to move from the point A by some little amount, right? That would cause a differential in the target. This is our linear estimate to how much the value of the function changes. What df does, it doesn't take points to points. It takes differentials to differentials. It takes vectors to vectors, you might say. It takes changes to changes. I don't know, kind of saying the same thing. Is that cool? Okay. All right. Now, here's a little innocent observation. Now, let's take the equation that we were just working with. The df matrix turns input differentials into output differentials. And now let's just divide by dt on both sides. And I don't want to get into formalities, and let's not worry about, technically we're also taking a limit. Okay, whatever. Now let's think about how to interpret this statement. What we have is a statement that the df matrix seems to be multiplying by this vector. Oh, hey, wait a minute. That's velocity. That's the velocity of my input point, dx dt, right? That says how fast and in what direction is my input changing. And then the output here, df dt. Well, again, that's a velocity. That says what is the velocity of the output? How fast is my output moving and in what direction? So this is another interpretation of the derivative, aka the derivative transformation. You can think of it as taking input differentials to output differentials. You can also think of it as taking input velocities to output velocities. So, very, very similar statement. In general, both of these fall into the category of what I would say it takes input changes to output changes. Interpret change appropriate to the context. My personal preference is to think about changes as velocities, because then I don't have to talk about approximations. This is all, limit as h approaches 0. This is all instantaneous, right? So the derivative matrix takes the instantaneous input velocity and then gives you exactly the instantaneous output velocity. So, anyway, very satisfying. Everybody happy? Okay, now this business down here is not a big deal. I just feel it necessary to point out that one of our other forms of linear approximations involved the gradient. It was like the first multivariable linear approximation we wrote down was with the gradient. And so you can play this same game of kind of moving things around. You can, again, it turns input differentials into output differentials. This time, though, by a dot product with the gradient vector, not a matrix product with a derivative matrix, but a dot product with a gradient vector. So I just want to point out that this is really the same thing if you think about it. Dotting with the gradient versus matrix multiplication by the derivative, they have all the same numbers in them. They're not exactly the same. One's a matrix, one's a vector. They're morally different things, but in practice, the numbers that make up the derivative matrix is a real valued function. The derivative matrix only has the one row. It's a single row that is all of the partials of that single variable output. That's exactly what's inside of the gradient vector. So this is really just kind of a notational alternative. So nevertheless, I feel it's appropriate to go ahead and write down that, dot product with the gradient does the same thing as the derivative matrix when it applies. It turns input changes into output changes. And the asterisk, the only asterisk here really is that this, of course, only applies for a real valued function. You'll notice we only defined the gradient vector for a real valued function. That's just how the pieces fit together. So don't think of this as an alternative. Think of this as a notational option in some cases. Morally, it's the same as this. So take your pick when you have a real valued function, but it's not actually different. Okay. How are we doing? Is everybody happy? Okay, so higher order partials. Well, I guess I'm getting a little ahead of myself. Let's talk about these properties first. There's just a couple of properties of derivatives that I need to recognize. Again, I have to remind you, tough choices and all that. There's limited class time, and you don't have time to talk about every single thing. The properties of derivatives they're pretty believable. They're pretty familiar looking. Take a look at them. Make sure you're comfortable with them. It's in the book. There's no real serious deep water that I'm gonna gloss over here. I do want to say something about one kind of subtle point, and that is when I say differentiation is linear. This can be misinterpreted. Let me talk about this a bit. Okay, so here's a derivative matrix. We know what derivative matrices do. They are matrices, so they multiply by vectors to give other vectors. So df, a derivative matrix, goes as a function from Rn to Rm, and being a matrix, it is linear. Now here's a completely separate point, completely separate from that. Not df, but d. Not the derivative, not the result of taking a derivative of a function, but the act of differentiation is also a function. The act of differentiation is something that you can do to a differentiable function. You give me any differentiable function, I can apply D to it, right? And when I apply D, when I do a differentiation of a differentiable function, the result is, as we know, a matrix. Right? So now let's take a moment to appreciate the difference here. The derivative matrix is a function from Rn to Rm. The act of differentiation is a function from the vector space of differentiable functions into the vector space of m by n matrices. That's a really different thing. Right? So when I say that differentiation is linear, I emphasize I'm not saying that all derivatives are linear. Yeah. Of course, they're matrices. Well, of course they're linear. That's old news, right? When I say differentiation is linear, I mean that this function is linear. The act of differentiation is linear, and specifically, what I mean by linear in this context is that if you put a linear combination in to the act of differentiation, right, then you get that same linear combination out. So said differently, you can do the linear combination before you differentiate. You can do the linear combination after you've differentiated. You're going to get the same thing either way. So let's see an example. What are we talking about here in practice? Rubber meets the road. Let's see here. I'm going to zoom out for space reasons. Here we go. Here's a function and its derivative. Now, again, that looks weird. You say derivative, you're thinking scalar, but not anymore, right? Now you see a function, multivariable function. The derivative should be a matrix. So there's a function and its derivative. Is everybody comfortable? Everybody happy with that? It's kind of a weird thing to choke down. So there's a function and its derivative. Here's another function and its derivative. And then now here is the linear combination. I took an arbitrary linear combination of these two functions and computed its derivative. Now, I checked my algebra on that, but I multiplied this out to get that. And then I took the derivative by the usual partial derivative rules and got that. So again, make sure you're good to go on all that. So did this work linearly? And the answer is, yeah. The derivative of the linear combination was this. The linear combination of the individual derivatives is that. And it's easy arithmetic to check that, yes, indeed, those are equal as they're supposed to be. Yep.
Does that mean that there's a matrix that can represent D itself?
Great question. So no. And let me explain. It's a great question. Let's think about how we would write a matrix that represents D. And I'm gonna flash back to Math219 here. When you want to represent something as a matrix, a linear transformation as a matrix, what you need is a basis for the domain and a basis for the target. Right, both of which are vector spaces, and then you write. The way you write the matrix is by looking at the images of the input basis vectors with respect to the output basis, and there's formula and a bunch of details, right? But that's the broad strokes. Well, here's the problem. The problem is that this is an infinite dimensional vector space. The vector space of all differentiable functions, it's literally infinite dimensional. There is no basis. So this being a non-Euclidean linear transformation, we are susceptible to scary stuff like this happening. And in this case, there's just no basis, so there is no matrix.
Okay.
Yep, it's a great question. Okay. All right, but if you were instead to restrict your attention here to just a finite dimensional subset of differentiable functions, then there'd be a basis, and then of course there's certainly a basis for this, and then you could totally write down the matrix representing differentiation on that vector space. Yep. All right. Okay, so see the book also for, there's a product rule and a quotient rule, various different cases. They're pretty believable. Take a look. Again, tough choices about how to spend class time, but they're in there. Make sure you're comfortable with them. Okay. And now we'll get on to higher order partials. This is, to a very large extent, exactly what you think. Y'all remember higher derivatives from single variable? If you have let's not worry about regularity issues. If you have a single variable function, you take its derivative, which is then also a single variable function. So you can take its derivative, right? We call that the second derivative. Okay, same thing here. If I have, let's say I have here a multivariable function. I can talk about its x partial. There it is. And notice, this too is a multivariable function of the same variables, right? I started with a function of x and y, and having taken the partial with respect to x, the result still a function of x and y. And so because it's a function of x and y, I can talk about its partial with respect to x or its partial with respect to y. And these are called second partials. Cool? Believable? Yeah. So there's a couple things to say about the notation here. Let's see here. Why don't I zoom back in so I can see better? So if you take the x partial of the x partial, I think that's a pretty believable notation. Let me remind you that fx says partial with respect to x. And then here, that says I'm going to take the x partial of that x partial. Okay. Now this other notation's a little bit weird looking. Where does this come from? It comes from the fact that we had, let's see, I'll do it like this. I had the partial of f with respect to x, and then I took the partial with respect to x of that. And so you see that there's a partial x there and a partial x there, and so those the notation arguably a little bit funny looking, but the squared does not mean that I'm literally multiplying it by itself. It's just a recognition of the fact that in the seeming denominator of these seeming fractions that we've written down, partial x is there twice. So don't overthink it. This is not a multiplication. And then in the numerator, there's a partial and then another partial, and thus the partial squared. Again, don't overthink it. It doesn't mean multiply. It's just recognizing it's there twice. Okay, so a little bit of a weird notation. Always bugged me when I was young. But it's just notation. I apologize. Okay, likewise over here, if you take the y partial of the x partial, so you would naturally write that like this, which gets shorthanded like that. Pretty reasonable, I think. Right? Likewise, we started with the x partial, and then we took the y partial of that. So I think this notation here also pretty reasonable. Now, let me warn you about an awkwardness, and that is that the first derivative that we took was the x derivative. The next derivative that we took was the y derivative. Notice that the colors are reversed. It's just the relic of the arbitrariness of the notations. When you say partial over partial x, we write that on the left side. That's just a convention. It doesn't mean anything. That's just how you do it. Whereas when we use the subscripts, we write it on the right side, and that makes them seemingly in opposite order of each other. That's just notation, but it is confusing, and so beware. Yeah, so that's why, it's yx there, but xy here. Okay. All right, same thing on the other side. By the way, you can compute all these partials. The x partial there ends up being this, and the y partial ends up being that. No sweat. Here's a kind of a little bit of an eyebrow raiser. If you look at the y partial of the x partial and the x partial of the y partial, mysteriously they're the same. What are the odds? Right? A little surprising, maybe. Turns out this is not a coincidence. This is often true, not always. As long as the functions in question are sufficiently regular, this will always happen. And what we mean by regular is that we need for a certain number of partials to exist and be continuous. This is kind of like continuous differentiability. You might say this is a higher order of continuous differentiability. And specifically, if the number of derivatives that you're taking, if the function is continuously differentiable up to that order, then you can reorder the differentials in whatever order you can take the partials in whatever order you like, and it doesn't make any difference at all. So said differently, this kind of thing here with this equaling that will happen as long as all of the partials, again, up to the appropriate order, are continuous. So, okay. All right. So now let's talk about what they look like geometrically. We'll start with the easy point of view, the easy question. Let's start with fxx. What is fxx? That says I'm going to take this function f. I'm going to view it as being a function of only x. I'm going to treat y as a constant. I'm going to take the derivative with respect to x, and then having done that, I'm going to continue to view it as being a function of only x. In other words, I'm going to continue to view y as a constant and then take another derivative. All right, well, did I really need to continue to view y as a constant? Why couldn't I just say I'm just going to view y as a constant for the whole calculation? Right? So really what you're doing when you're taking a second partial with respect to x is you are making y constant, looking at the cross-section for that constant value of y, and then you are taking a derivative with respect to x followed by another derivative with respect to x. In other words, you're taking literally the second derivative of the single variable function of x. And we already know what second derivatives do. Could they tell you about concavity? As I have it drawn here, the concavity is down. That means fxx is negative. Per this picture anyway. So it's exactly what you think. Concave down means negative, and concave up means positive. And then likewise, if you're talking about in the y direction, then you're just setting x equal to a constant. You're looking at the cross-section in the x direction. Sorry, I guess you'd say cross-section in the y direction, because x is constant. You are then taking the derivative with respect to y twice. That's a second derivative. Second derivatives tell you about concavity. Concavity, up is positive, down is negative. Here, this cross-section is concave up. Fyy is positive. Everybody happy? So I'm going to call this exactly what you would think, right? Second partials tell you about concavity. Okay, now, but there's a twist. These are what we will call unmixed second partials, because I did the second partial and the first partial are with respect to the same variable, right? Xx and yy, etc. So that's not always the case. So what if you were taking the x partial of the y partial of a function. What does that look like? And is that geometrically familiar from Calc 1? And no. There is no version of this in Calc 1. There's not enough space in the domain to have two different directions with respect to which to take derivatives. So this is completely uncharted territory. Do not think in terms of this being analogous to anything. It's not. So how we deal with this is tough. Thinking about this geometrically, and I'm going to have to zoom out for the space. Let's take this one step at a time. I'm going to start off by thinking about the y partial. How do I geometrically view y partials? No problem. This is we've already got an existing interpretation. The y partials are the slope of the tangent lines in the y direction. So, for example, at this point right here, moving in the y direction from that point, maybe the tangent line, something like that. So whatever the slope of that blue line is, whatever the slope of this line is, that's the value of the partial of f with respect to y. Is that cool? Now I could do the same at other points. At this point here, as I move in the y direction, maybe the tangent line would be something like that. I don't know. You'll notice that I didn't draw the surface on here. I didn't want my surface to kind of get in the way of... let me rephrase that. I tried to draw with the surface on here, and the picture just got confused. Right? I got in my own way, as it were. Anyway, but you could imagine there being a surface where this is what the one tangent line looks like, and this here is what the other tangent line looks like at these different points. And then again here, as you go in the y direction, maybe it's got a steeper tangent line, etc. Over here, maybe it's like that. Over here, maybe it's even kind of like that, let's say. Okay, so all I've got here is a bunch of instances of, geometrically, what does the partial with respect to y look like? Okay. Now, when I take an x partial of that, how can I, on this picture, understand the x partial? And it's going to be tempting to say that it's a slope in the x direction. We can't. We've got to be really careful about this. We're taking the x partial, but not of f. Right? We're taking the x partial of this other function called partial of f with respect to y. I don't have a graph of the partial of f with respect to y. I have a graph of f. So I can't interpret this x partial in terms of slopes. I just can't do it. What I can do is take a different geometric interpretation of x partial as x partial says, look, as you move in the x direction, how fast is the function changing? And so this is that other interpretation I want to take. And here you go. In the picture, I can imagine that I'm moving in the x direction like so. And as I do that, how are these blue slopes changing? As I have it drawn here. And I would point out that it seems anyway that, here, the blue slope, partial of f with respect to y, is pretty negative. Looks like about, -2. And then here it's -1-ish. And here it's about, -0.5. And then here it's about 0. And then here it's about +0.5. Hey, you know what? All of these blue slopes, all of these partials of f with respect to y, all of these things that I'm taking the x partial of are increasing. So these things here, these y partials, are going from significantly negative to slightly positive, and that is an increase, and so I'm going to say that this x partial of this y partial is positive, because we're taking the x partial of things that are increasing. Does everybody follow my reasoning there? It's geometrically pretty hard to visualize. So, okay. All right, so what's the upshot to this then? What sense do I make out of this mixed partial? The x partial of the y partial. What aspect of this picture here is the giveaway that these y slopes are becoming more positive as I come out of the page, right? So they're negative here. As I come out of the page, they're becoming more positive. And geometric appeal, it's like I'm putting a twist into the surface. Everybody kind of see the twist that's happening there? So that's what mixed second partials look like on graphs. It's hard to visualize. But mixed second partials represent a twisting of the surface, specifically the graph. And sometimes that's called torsion. Just a word, don't worry about it. All right. Okay, is everybody happy? Okay, moving along. So now I previously noted that there would be some jumping around in the syllabus. So in other words, I'm not going to go straight through the book. Of course, first example of this, we did section 1.6 before 1.1, blah, blah, blah. Now here that we have finished section 2.4, I'm going to jump up real quick to chapter 3. And we're going to do section 3.1. And then we're going to come back into chapter 2 and resume with 2.5 and sort of take it from there. The reason for this will become clear later. Basically, I need to be able to make an interpretation of the derivative of a parametric curve when we start doing the chain rule. The chain rule is going to be our next thing back in chapter 2. So let's just go ahead and do it. Reminder, parametric curves. Right, a parametric curve gives position as a function of what I'm going to loosely call time. Right, so it's a vector valued single variable function. Isn't that cool? Vector valued single variable. Okay, and of course you might write it like this, for example. So let's write down its derivative matrix. Now this is just a matter of doing it. There's several outputs and thus several rows to write down, but there's only one input and therefore there's only one column. In fact, if you think about it, the partial derivatives that are these entries are, it's a single variable function. There are no other variables to hold constant. It's only one variable. So these aren't even partial derivatives. In practice, they are effectively single variable derivatives, and thus you'll notice the D instead of the partial symbol. Right? That's not a mistake. These are literally D's. These are literally straight up single variable derivatives. And now I'll point out that what you have here as is a column vector of derivatives. You might say instead it is the derivative. It is the derivative of the vector valued function x, because we're taking the derivative one coordinate at a time of all of the coordinates of the parameterization x. Okay. And a single variable derivative is something we have a different definition of. Single variable derivative is defined as a limit. And this is, again, hopefully familiar. You saw this back at the beginning of Calc 1. And so there you go. So this is going to help us make sense out of the derivative of a parametric curve to see it in this form. And so, for example, let's consider a starting point somewhere on the curve, some value of t, whatever. And then we have to, look at where are we h seconds later. We're at a different point there. And then we subtract you got our numerator. Our numerator then, you notice, is a vector. Right? You might call that a secant vector. Y'all remember back in Calc 1, and they talked about secant lines? Right? This is a vector, so I'm going to call it a secant vector. Okay. And then let's see here. Now we've got to, we've got to divide by h. So, okay, dividing by h, we're going to get something that I'm going to, at least for the purposes of what we're doing here, I'm going to draw that as being a little shorter because we're dividing by h. And I haven't said h is small yet, so I'm going to momentarily pretend h is a little bigger than 1 at least. But now we take the limit as h approaches 0. And as you do this, as you take the, I've run out of colors, as you take the limit as h approaches 0, several things happen. On the one hand, this point gets closer and closer to the base point. That means that this vector, anyway, my colors are shot. But the difference vector, that is that numerator, is going to get shorter and shorter. But I'm also going to be dividing it by an h that is smaller and smaller. And so what's going to happen then is, instead of getting secant vectors that are like this, I'm going to be getting shorter vectors divided by smaller denominators that shouldn't have too much of an effect on the magnitude. But as these points get closer and closer, our secant lines become more and more like tangent lines. Oh, I missed. I want to get this. Yeah, there we go. More and more like tangent lines. Everybody buy it? So the appeal I'm going to make, and this is just a sort of a geometric appeal, this resulting vector, the derivative vector here, that derivative vector points in the direction that the curve is going. You might say it's tangent to the parametric curve. Take your pick. And now let's think about what is the magnitude of it. The magnitude is, if you think about it, is the magnitude of this displacement vector is just a distance. H, the denominator, represents the elapsed time between those 2 points. We have almost exactly distance over time, and that's speed. Right? So altogether then, our vector, our derivative vector, it points in the direction the curve is going. Its magnitude is equal to the speed. Where have we heard that before? That's the very definition of velocity. Velocity is a vector that points in the direction that you're going and whose magnitude is the speed. Straight up definition of velocity. Is that good? Okay. So, kind of a neat fact. Now, I think it's worth emphasizing. Notice that this derivative here is not a slope. Right? It better not be. It's got to be a vector, just algebraically structured. I mean, you can see it's a vector. Right? So it wouldn't make any sense to be a slope. And it isn't a slope. It's a velocity. How we doing? Everybody happy? So notice, yet again, derivatives get different interpretations, different geometry, right? Depending on what kind of a picture are you looking at. To revive the language that I was using a couple of days ago, the calculus of parametric curves that we're seeing here is very different from the calculus of graphs, where the partial derivatives really were slopes. Asterisk details, right? But the calculus of graphs, the calculus of parametric curves, likewise, how do you interpret derivatives on level sets? So the calculus of level sets, all geometrically completely different. So make extra double for sure that you are comfortably proficient at looking at your picture and knowing what kind of a picture it is. Is this a graph of the function whose derivative I'm interested in, or is my function a parameterization of the curve, or is this a level set? What kind of a construction are you dealing with before you interpret? And if you apply again the wrong calculus to the context that you're in, you're going to get a dramatically wrong answer. Okay. All right. Likewise, acceleration is the derivative of velocity. This is a physics thing more than anything else. Let's see an example. Suppose that you are given a velocity, not a position, but a velocity as a function of time. And then some starting point. At time equals 0, the position is 5, 6. All right, so given this information, what is the acceleration of this moving particle, and what is the position as a function of time of this moving particle? Okay, well, so acceleration. To get acceleration, we take the derivative of the velocity to get acceleration. And that's easy computation. Reminder, I'm assuming that y'all are good with single variable calculus and you know how to take the derivative, coordinate by coordinate. Boom, there you go. Everybody happy with that? Yeah. Okay. Now, what about position? What is x as a function of time? Position is a function of time. Well, think it through. Velocity is the derivative of position. Therefore, position is the antiderivative of velocity. Right? So I'm going to need to take my velocity here that was given, and I'm going to need to take an antiderivative with respect to t. I'm going to have to take an antiderivative of that thing. And, of course, antiderivatives, just like derivatives are taken one component at a time, antiderivatives are taken one component at a time. And so, again, I remind you, single variable calculus, I'm going to assume that you're good, right? That you're strong and proficient with how to do antiderivatives. So, make sure that you're all, brushed up, polished up on all those skills. And, when I say all, I mean, you definitely want to make sure you're really good with substitutions, really good with integration by parts. Obviously, all of the standard, polynomials, right? Exponentials, right? Those are all pretty straightforward. And various little tricky cases. There's a category that sometimes is called trig integrals. So, for example, you make sure that you can do, like, if you find yourself looking at integral of sine squared times cosine cubed, make sure you can do those. That comes up. And there's just little tricks to know. So, anyway, that's all single variable calculus. Make sure you're good. Okay, now some more details. When you do an antiderivative, there's always a plus c. Because there's a plus c in each one of the components, there is effectively a plus c vector that you can just put on the outside of that antiderivative. Now, how do you compute that? Let me tell you what not to do. A lot of students mistakenly seem to think that is always equal to the initial condition, and that is wildly wrong. It's really, really wrong. Let me show you the right way to do it first, and then I'll try to explain why it is that this, where this nonsensical mythology came from, and I have a theory about that. But anyway, first of all, how do we actually compute it? We plug in the initial value. So we're going to literally just plug in t equals 0. And if I do that, plug in t equals 0 into there, and there, and there, and here. Right, don't forget what this formula is over here. That's telling you position. So plugging in t equals 0 means that I need to be looking at position at time equals 0. And conveniently, I can compute all of these things. Position at time equals 0 is given. Right? All of this stuff here is just algebra. Just literally plug in t equals 0 and see what that turns into. Right? And then, of course, c comes along for the ride. We haven't really done anything with that yet. But the punchline is that just by the mere act of plugging in t equals 0, what I've got then is a nice little equation in which I can solve for c. So everybody see how that works, right? And hopefully it's familiar. It's morally equivalent to what you did in Calc 1 classes. Excuse me. Okay, now where does this mythology come from? That somehow this is always equal to that. And here's my theory. Very often in high school calculus classes, they like polynomials. Let's just keep everything polynomials because other kinds of functions, the integration's hard, right? And so for a lot of students, the only examples of this that they have ever seen are where all of this was a polynomial. And if you think about it, if you take a antiderivative of a polynomial, what you will get will always be a polynomial that has a factor of t in every term. And if you have a factor of t in every term, then when you plug in t equals 0, and there's a factor of t in every term, then you will get just 0 here. And if you get just zero there, then in that case, now that's a an exceptional case. In such a case, c really is the initial value. So basically, I think this mythology is a relic of I'm going to call it lazy examples in high schools, right? And so anyway, be aware that is absolutely not valid, and it is wrong to just say that is equal to that. And so we're out of time. And we'll pick up, real quick, take a look at this theorem right here. It's very straightforward. It's basically a product rule of parametric curves. It's exactly what you would think. And so we're done now with 3.1. And we'll pick up next time with the chain rule. Y'all have a good day. See you later.